Welcome to Ampcontrol's webinar, Technical Requirements of ASNZS2081 Compliant Relays. Your presenter is Terry Brown, Ampcontrol Product Manager, Mining Electronics.
We'll be there. Okay, basically the standard falls into two parts for any relay. It's firstly the general requirements which all relays need to meet, and we'll go through those first up. And then secondly, the individual requirements for each relay type. And the relay types we'll be talking about are earth continuity, earth leakage, earth fault lockout, and NER monitoring and frozen contactor protection. Normally earth fault lockout and frozen contactor go together, and we'll see why as we talk about the requirements of the standard. So on to the general requirements, and in addition to filling the various type specifications for each relay, the standard calls up a number of things. Firstly, that the relay itself should be fairly robust and of reasonable construction, and the connection arrangements also need to be fairly well let out, fairly well labelled, and so there's little chance of a installer making a mistake. And normally this requires a manual to go with it, so a manual or a data sheet so that it's easy to see what connections are what. The next requirement of the standard is that if the relay does fail, it fails to a safe position so that it is not causing a problem, that the problem it causes is a safe one, not an unsafe problem. And to go with that, relays, the latest relays we produce, we either have some sort of SIL information such as safe failure fractions or mean time between failures, something that a customer can use to work out his SIL ratings or his basic reliability of the system he's putting in, or the relay he's putting into a system. The other thing called for is a minimum service temperature and humidity. Basically, the relays in the latest standard tend to head from 0 degrees to 60 degrees. And we fairly well test that, and we fairly well test at all those levels, and while each relay may not individually be tested at those temperatures, there's certainly a preliminary test done to make sure the design is capable of working at those temperatures. Interference to immunity, this is a fairly well updated and new requirement to the relays, so that particularly talking about noise immunity from various inputs of the system. The relays have to go through a fairly rigid test now for various noise interference immunity, and so all relays are put through that before we release them. Vibration, shock, and bump immunity is another one. Luckily, our relays are fairly small, so they don't really have any great problem getting through vibration and shock, but it's something that the relays are put through initially, at least, when we're type testing them to make sure that they meet the standard. Minimum ingress, so the relays are called for a very minimum of IP20, which basically means that you can't touch any live parts with your fingers. And most of our relays are either that or better than that. Relay contact ratings, this is a hotly disputed factor, but the standard says that if the relay manufacturer says that the relay will withstand 5 amps, then on our relay we have to specify a 1 amp maximum. So they give you a safety factor of 5 in the relays. Now, the general requirements also include fault indication, so that you need to visibly be able to tell the state of the lead from outside the relay. If it's a fault condition, what type of fault it is, if the relay is okay, if there's power to the relay, and that's provided on all our relays. There should be a provision for restricting the adjustment of the relay so that not anyone can come up and change the settings on the relay. There are some specific requirements. Parameters should not be able to be set outside the limits of the standard. So, for instance, with earth leakage at the moment, common maximum setting for a time delay is 500 milliseconds, whereas previous standards you could go out to 1 or 2 seconds. We're now restricted to keep the relay so that it cannot be set anywhere outside that limit. Now that can be done two ways, either these days more likely with a password, an ability to do it, or you could physically lock and stop people getting in to make those adjustments. And that's how that's done. Specification of content including in the label. Okay, so the specifications of the relay basically need to be on the relay, on the label, and they're fairly well set out in the standard. The tolerance of the supply, the latest standard says that relays should operate quite all right from 75% to 120% of the nominal voltage, and with a proviso that the relay should be able to run for 2 seconds with 50% of the voltage in. So our relays these days tend to be 24 volts DC, which means that they should be able to run for at least 2 seconds at 12 volts, at 50% of that. And most of them, or all of them, do, certainly the ones to the latest standard. Withstand ratings of power supplies, etc. Once again, just the ability of the relay to withstand any voltages it's likely to get on. The other requirement of the standard is that software is to be limited so that a third party can't get hold of your relay and change the operation of the relay by changing the software. And once again, this can be done inside the relay and can be done by various software techniques. Okay, let's look at some of the particular relays now. And the first one we'll go for is earth continuity. There's a few new requirements in the standard these days, and we can have a look at those here. We look at a typical relay just sitting there, the MEC1, which is a metalliferous earth continuity relay. But the earth continuity protection, really all it does, or what it does, is monitor the impedance between the pilot output of the relay and the earth return. So you're looking at it down a trailing cable and keeping sure that the earth impedance remains within an allowable range, so that in doing this, the maximum touch potential that can appear on remote equipment would be in a safe region. The other thing the relay does do is allow for remote stop and start, and we'll talk about that a little later as we go through the system. Okay, relays basically test the pilot earth impedance prior to energizing the relay, and it continually monitors this impedance between the pilot earth loop. So you're basically, that's looking at the series resistance. If you look at the circuit down below, we have a relay sitting here, a pilot output where we measure the series resistance through a terminating device back to the earth of the relay. The series resistance, and the other possibility is a shunt resistance that's measured, and the series resistance these days, the standard hints at being allowed to adjust that value. It was set at 45 ohms in an earlier life. It's now an adjustable value that can be set, and this is to limit what the earth impedance may be. You may have a very good system with low pilot impedance and low earth resistance, then you may want to set the pilot earth loop down to 10 ohms, so the maximum resistance the earth can get to is 10 ohms before the relay will trip. In the cases of long cables, we have an instance in Queensland where we have 5 or 6 kilometres of cable connected, where the pilot impedance itself is somewhere near 70 ohms. So your relay needs to adjust to take care of that as well. Shunt impedance is basically kept, that's the resistance between the earth and the pilot itself. is a threshold of 1K. So we typically trip the relay if the impedance falls somewhere near 1200 ohms, would be our standard tripping thing. Okay, the standard also calls up that the relay should be able to trip within 100 milliseconds, and that you can have a provision to delay that trip time if you want to up to a maximum of 500 milliseconds. The original idea of the maximum 500 milliseconds is that that's about the time that the fastest time someone could pull a live plug out between cables, and therefore that would expose live connectors, and by tripping within that time you eliminate the possibility of doing that. Most of our systems in the field are probably set to about 150 milliseconds. Usually the quicker the setting, the safer the relay or the system is. Another requirement for the earth continuity relay is that if you have a remote start, and on the next page we have a drawing where we show how it's connected, that if the remote start button is stuck in, then the relay will trip after 15 seconds. And that's done on our latest relays. Earlier relays didn't take that into account. Certainly the latest standard requires that. The other thing is with the earth continuity is it's one of the few relays that you can have a non-latching trip, so that the system can trip and then take power as soon as the fault is removed. The new standard says that, well as having that, you should be able to latch the trip. So some people may feel safer if they latch a trip whenever it occurs, and that ability is on the relay as well. Okay, and the final thing is that, an external reset, of course. If it's latched, you have to provide an external reset. And there should be no possibility of overriding any trip condition by holding the reset button in. And that's something we check fairly rigorously as well. Okay, so here's a typical setup of the circuit. A power supply, 24 volts AC, DC. Certainly the industry seems to be heading towards looking at limited voltage for the control voltage, so a very safe voltage, 24 volts is something we're settling on, and most of the industry is now. A reset button, that's the external reset, is held there. The pilot lead and the earth lead are the basic interface to the outside world. So in most cases we recommend a fuse of some type, just in case there's a fault in the cable and high voltage is connected to this point. There are other protections, but a fuse is recommended. A remote stop is usually just a button along the pilot lead, which trips the relay fairly quickly. And here's the remote start condition. It's a 100 ohm resistor with a switch put across the resistor, so that the relay sits in an off or non-operating condition when it's asked for a remote start condition. And when this switch is pushed and shorts out the 100 ohm resistor, the relay then activates its output and takes up its position. That button then should be quickly released, and one of the standards requirements is that if it's not released within 15 seconds, the system trips. And once that's tripped, then you've got that 100 ohms permanently in the circuit, and the relay is now looking, say if you set it to 10 ohms, it's looking for 110 before it will trip. And in this case, a diode's used for termination. A 1 amp diode. Normally we recommend probably a 3 amp diode there, but 1 amp will do in most cases. And a 1000 volt 1 amp diode is a fairly robust diode. The other inputs here, of course, are just other input outputs are outputs. The control output usually going to a main contactor, and then some sort of lamp output as well to let you know that there's been a trip on the circuit. Okay, so let's just run quickly back to looking at the relay itself, and you'll see just some of the front panel type things. There's a status light telling you that it's got power and that it's running okay. There's a trip level setting, so you can now set the trip level to 10, 15, 20, 25 ohms, etc. A trip time, setting the time for the trip or the delay that you want. A remote start button, it can be either on or off, and a latching button can be on or off. A healthy light to tell you the relay's healthy. Then the type of trip, a short circuit or an open circuit trip, and a start timed out indicator as well. They're all sitting there on the relay, and you can see the input outputs are labelled here. So that's a relay that complies very well to the latest standard, and therefore it has that on the front of it with the relay. Okay, I'll head back to where we were. And we'll look now at the requirements for the earth protection and earth leakage standard, and we'll go with that and see how we're going. We have a number of earth leakage relays that have been in the field for a long time, and sitting here as an ELV, it's a relay that has extra functions of being a wide bandwidth, so it can be used with variable speed drives very effectively. Okay, the earth leakage protection devices monitor the magnitude of any currents which find their way back to the phases other than through the phase leads themselves. So any earth leakage going through the system will be detected, and if they reach the trip level, the system will be tripped. And this is the way of assuring touch potentials. Of course, the touch potential is a function of two things: the resistance back to the earth and the current flowing at the time. So the earth leakage has the function of detecting the current and also limiting a time that current can be active for. So the earth leakage is usually set to the lowest trip time that practically can be used. So there's two ways of doing it. You can either have a core balanced, or you can have a star point monitor, so with a toroid around one of those, either the three phases or the star point lead, you can measure what current is heading back into the phases that went through Earth. Okay, the standard says the protection device and current sensing transistor shall be capable of accurately sensing the initiating current, and within the range of fault-wise currents from 0.1 to 5 amps. There's certainly a change from some of the previous standards, but it is really on the same line. In this case, the accuracy of our measurements has to be plus or minus 10%, and this is where the standard has changed. Previously, it had to be, very early, it just had to be less than the set current, so it could be anywhere. Then it had to be within 20% of the set current, and now we have plus or minus 10%. And where they have tightened up, of course, is in the time, so that while the current is plus or minus 10%, the time is certainly a narrower requirement these days. Okay, so they also mention that care should be taken to make sure, if you have a 5 amp earth limited system, that the maximum setting you set the relay to is 500 milliamps. So there's a 10-to-1 ratio there. And they've pointed this out because they've allowed us to go from 0.1 to 5 amps. They just wanted to make sure that if you have a 5 amp limited system, you don't go any higher than 500 milliamps. And they should be set as low as practical. Now, the ELV relay, which I talked about before, has a particular curve, a response curve, which allows you to set very low currents without getting false tripping, and that's one of the advantages of that type of relay. Okay, instantaneous trip time. Basically, it's saying the relay must be able to trip no greater than 50 milliseconds, and typical relays, the VSD guard, for instance, trips about 36 milliamps. The ELV relay was somewhere around about 40 milliamps, so they're well within that requirement. And also provided in the standard is that the maximum delay is 500 milliseconds. Now, it's quite different to some of the earlier relays we've sent out with 2.5 seconds or 5 seconds delay. Now the new standard requires a fairly strict and 500 milliseconds. So on the relay, you just simply can't set any more than 500 milliseconds. Also, the standard has a requirement to make sure that the transducer is in circuit. And so basically we have to check that the toroid is connected to the relay, and that can be done two ways. You can either have a loop going out into the relay with a small current or frequency in current that you can check to see if it's there, or in the case of the ELV, LD, we put out a high frequency signal out to the toroid and make sure that there's an inductor connected to the actual relay itself, so we can check that it's within circuit. The standard says that you have 5 seconds in which to make that decision, and that time gives you time to get away from any false trips or any slip ring sort of problems that may occur, or any small variations that occur. You've got a little time to make that decision. The relay must have an external reset. The fault protection device shall latch when tripped and remain until it's reset. Certainly the earth leakage relays all latch. And you must not be to override it, which is a sensible requirement as well. And all faults shall be manually reset. They're not permitted to automatically reset these relays. So earth leakage is considered a fairly important and high priority device that shouldn't be automatically reset. So here's a typical application where we have our power again. In the case of the ELV, for instance, it's quite a wide input. We go from 24 volts to 168 volts DC. We also can take AC into it as well, as shown here. 24 to 110 volts, so it's a fairly useful relay in this sense, particularly for older installations that may have a 110 volt supply. The relay basically has either one of two transducers. Either the toroid is around the three phases, or an alternative position for the toroid is around the neutral to earth link. And you can see here there's also a test loop put in here so the relay can be tested. Its SIL ratings or its failure safety fractions also depend on the relay being routinely tested, and that's why these are drawn in the circuit. And also some of the standards for mining call up routine testing either once a day, once a month, so you can check the operation of the relay. The toroid, yes, the inputs are here. The outputs pretty much like the other relays. You have a main contactor tripping point and a indicating output as well. In this relay we have a 4 to 20 milliamp, which can be used to monitor the leakage in some cases. Critical situations may need that. External reset, as mentioned before. A leftover from previous relays, a non-fail-safe link. It's not used in this relay. And as I mentioned before, the ELV has a number of bands. It has 3 bands. It has a narrow band if you link 11 to 12, so that's 50 hertz only. This is a frequency band. A wide band if you link 1 to 3. You're then measuring from, wide band is 2 to 3. You're then measuring 0 to 10 kilohertz, or a few hertz to 10 kilohertz. It also has a weighted band, which is linked 1 to 3 or leaving the links off altogether, and that gives you both a wide bandwidth but with a reduced sensitivity at high frequency. This stops any unwanted trips. It still gives a safe system, and if you want to know more about that, the manual explains that fairly well. Okay, let's move on, and we're looking here at the earth fault lockout relay. This is one of our new relays to come out that meet the standard, and one of the few that does. And basically this is the EFL relay. The EF relay now has been in the field for a few months and fairly positive feedback at the moment. It performs two functions, but the function we'll be looking at now is earth fault lockout. And basically the application is the earth fault lockout monitors the impedance of each phase before the outlet is energized, and if the impedance falls below a certain value, the device will inhibit the closing of the contactor. So it's basically stopping you from putting power onto a short circuit or a damaged cable, and having a major incident as when you turn a system on. And as I say, this is typically connected to a frozen contactor. We just have a look at some of the thing here. This relay has an inbuilt barrier to connect to the high voltage, and it's up to capable of 3.3 kV. At the moment, we have a 1,000 volt system up and running. The 1,000 volt barrier will not only look at 1,000 volts, it looks at 500, and it looks at 240, and looks 110 as well. So there's a voltage switch here that you can switch to whatever voltage range you're looking at. There's also a back EMF time set at this switch. The frozen contactor indications are here, and we'll talk about those later. The earth fault lockout problem faults are displayed in this area here. Once again, there's a status light to tell you how the relay is going, and a little information on the side of the relay talking about the relay's operation. Okay, the requirements for the earth fault lockout. It's basically to prevent the circuit, as I said, switching onto a short circuit. And in previous standards, the trip level's been set at somewhere like, say, for 1,000 volts, 10 k ohms. Now the standard's increased it to 1 megohm for all voltage inputs, so that the relay looks, and if it finds a resistance less than 1 megohm, then it will stop the contactor from closing. The standard says you can have higher values than that, but 1 megohm is a fairly reasonable upgrade from 10 k ohms. And the standard says once you have detected this and tripped, then the relay has to latch and can only be reset by an external reset. Okay, now the standard also allows for a second high voltage output. Now some of our more complicated relays like IPMs or IPCs, integrated protection relays, will, after it's done a first low voltage test, it'll put out a high voltage test and do an insulation of the cables and test that. With the cheaper relays, that's considered not required, and also would increase the price dramatically. And so it's not done in the cheaper single function relays. Some of the requirements for latching, so there's an external reset, which we do have, and they latch when they trip, and they cannot be reset until an external reset has set it. And once again, you shouldn't be able to override the latching or the trip by holding the reset button in. And all trips have to be manually reset, no automatic resetting. And so here's a typical connection to the relay. High voltage interface, a barrier. Now that can be external or internal, and the one that was shown in the picture was an internal one. This is also available in external, and that's obviously to go between the high voltage and then reduce the voltage to a much more manageable voltage, somewhere around a couple of volts, into the relay itself. Basically, the relay has to monitor what the main contactor is doing, and it does that through the auxiliary input contact. It also has an output for the main contactor to turn it on and off. There's also an output, because this is a frozen contactor function, can head to a circuit breaker as well to get the power away from the main contactor. Yes, in the case of frozen contactor, there's also another input here called a run input, and we'll talk about that a little later on. Power supply, 24 volts AC DC, keeping with our standard sort of connection we're using these days. Trip indication for earth fault lockout coming out here, and one for frozen contactor there. The external reset, which is for the earth fault lockout. This relay also has an under voltage trip, but I'll ignore that at the moment. That can be used or not used. And then this gives you a little bit more about the circuit needed to set it up and run it, and get the thing operational so that it meets all the requirements of the standard. Frozen contactor, so that's really our next version. We'll look at that fairly quickly. Same relay, we've talked about it. A frozen contactor basically monitors the position of the contactor and looks for unwanted voltages, or the wanted or unwanted voltages on the load side of the contactor. If it finds the contactor is in a position where it's not meant to be, like there's voltage on the line yet it's meant to be open, then it will trip upstream, so that's where the circuit breaker output comes in. And typically it's connected with the earth fault lockout. So we have a new standard is calling up that the device should trip at if it finds 20 volts AC or 60 volts DC on the load side when the contactor is meant to be off, when it's meant to be in the open position. So it's giving protection that there's no unexpected voltage, or there may be a frozen contact, or there may be something wrong with the circuit giving unexpected voltages. Yes, it's meant to, as it says there, the protection device shall design to initiate a trip of the upstream circuit of the interrupting device. And if it finds the relay is not performing, or the contactor is not performing as it's expected to do. So, if the relay hasn't followed an expected signal, so the relay was told, the system was told to start and the contactor meant to close, the frozen contactor finds that there's no voltage when there's meant to be, then it will de-energize the circuit. Okay, so requirement for operating time, basically the operating time for the relay itself is about 1 second for normal operation, or it is not to exceed 1 second. There is a slight caveat here that if you're turning off a load, then you're given from 1 to 20 seconds to dissipate the back EMF voltages. So one of the controls on the relay was to allow you to set that back EMF time, where the frozen contactor relay ignores the output until the 20 seconds has elapsed. Now, the frozen contactor latching is a little different to the others. Obviously the protection relay should latch, which it does. And even if you turn the power on and off, you shouldn't be able to recycle that. You shouldn't be able to reset it. So the frozen contactor has in most relays, a battery, and in the case of the EFL, it has a super cap, which holds power for a few weeks, letting you know there's been a trip and allowing you to manually reset it from the relay face itself. Now, the reset facility has to be integral to the protection device, meaning that you've got to open whatever cabinet it's in, check the contactor to make sure it's functioning okay before you go and hit that reset. And obviously the power will be off if it's in a trip state, so the cabinet can be opened. That reset can then, if you've checked the circuit, everything is okay, you can then reset the relay, and it can be reset without power on, so it's a safe thing to do. Close the cabinet and then start the system again. pretty much the same circuit as we've looked at previously. Here the frozen contactor makes use of the MCI input and also this indication to run input, just to make sure there's either a logical fault if it was told to start and there's no voltage, there's a logical fault somewhere, or if there's a voltage on the end, then it's an electrical fault when there shouldn't be. So the relay gives you those indications. And of course the frozen contactor push button for resetting is on the relay itself. Okay, NIRM integrity monitor. Well, this is one relay that Ampcontrol themselves don't make. We do supply a relay though through a third party, and these relays are in the process of being redesigned at the moment, because I don't know of any relay that exactly meets the current standard. The current standard has changed from the older standard, and it requires monitoring devices to do a number of things, and we'll go through those now. Usually they're associated with an earth leakage function as well, because while you're monitoring the neutral to earth resistor, you may as well look at the earth leakage going through that resistor, and you can detect at the same time. Okay, so basically if it does find a problem, then it trips an upstream relay to take the power off the system. And the requirements are that any current flowing through the earth shall not be affected by the operating values. So the new protection relay has fairly strict in one sense. It's monitoring the neutral earth resistor, and in this case we're looking for any increase in impedance, say 100% increase, or any reduction in the resistance, and they look for a maximum of 50% reduction before the relay is tripped. And this is making sure that that current limiting device is within reasonable specifications. And it's given 10 seconds to trip because it's not a usual fault, and it's a fault that's not likely to occur in an instant. There's time to actually look at that resistance, measure it carefully, and then decide to trip within a 10-second period. External reset, of course, is required, and the fault must be latched and not possible to override it again, as similar to our other relays. And the other thing is the actual measuring device, the relay itself, should not affect the impedance of the neutral earth resistor by any more than 5%. So basic circuit sitting here, we have neutral earth point and the neutral earth resistor, limiting resistor, and from this point we're monitoring exactly the resistor itself through the bender device, and here's the interface that interface across there to do the measurement. The bender device has a few displays associated with it, and is capable of opening the main contactor if that resistance is incorrect or not within the value it should be. Okay, that's basically where we are through the circuit, and yeah, I hope you've enjoyed that, and if there are any questions, please type them, and we can attempt to answer them. Otherwise, thank you very much for attending and listening, and I hope to see you again in the future.